Hello, we are live. Thank you for joining us again this month on another developer live stream. Appreciate you taking the time to join us. Before we get started, wanted to just share that there is, for those of you who are interested attending GTC in Paris, which is happening in about a week, we can throw in a slide, or actually a link for those who are interested in signing up. That's kind of a quick housekeeping, but to move on to why you're really here today, we're joined today by Kefeng, who's a compute architecture GPU deep learning engineer. And today in this session, you're going to learn from Kefeng and a few others about how we push DeepSeek R1's min-latency performance to a boundary based on TensorRT-LLM and SOTA technologies on Blackwell GPUs. So, Kefeng, I'll pass it to you.
All right. Thanks, Zach. And good day, everyone. I'm Kefeng Duan. I'm here on behalf of the great teamwork to report out how to push the latency performance boundary for DeepSeek R1 model on NVIDIA GPU. Its agenda today. First of all, I will introduce some motivations, and then followed by a summarized feature list. And I will give some details about our configurations and key features. And finally, about our future works. First, it's the motivations. We have two motivations. The first is, of course, we want to optimize the latency for reasoning large language models. And what's more, we want to explore the methodology to push the latency boundary on NVIDIA GPUs based on TensorRT-LLM. It's a summarized features list. And in this table, we have listed all optimization items. And these optimizations have helped us to boost the perf of DeepSeek R1's mean latency from 67 TPS per user to 368. And I will give more details about how do these features help us to keep the world record all the time. But before that, let's give some details about the configurations. In this slide, we have shown a simple layer-wide diagram of DeepSeek R1's model. And for the main model, there are 3 dense layers and 58 MOE layers. And besides the main model, DeepSeek R1's checkpoint has provided an MTP layer weight. And based on our exploration, if we can extend this MTP layer weight to 3 MTP layers with an autoregressive style, we can achieve the best perf based on speculative decoding. That is to say, for each generation phase, we will have 4x tokens, 1 from batch size 1 and the other 3 from MTP layers. Our mean latency workload is shown in this slide. Our batch size is 1, and our input sequence is 1K, where output sequence is 2K to fulfill the requirement of the reasoning model. Our main hardware platform is DGX B200. There are 8 GPUs connected by NVLink. But most of our optimizations can be applied to the other type of GPUs of NVIDIA. We have explored a mixed precision within NVIP4 and BF16, and the details of this precision are listed in the first table. For example, for all attention modules, which consist of GEMM layers, Q cache, and attention kernel, we have introduced BF16 precision. For all FFN layers in my model, such as the 3x dense modules FFN layers and the experts of the my model, we have introduced NVIP4 precision. And for the last 3 MTPs FFN layers, we keep BF16 precision. And for router GEMM, we have kept BF16 input and IP32 output to guarantee the high precision. The last configuration is about the parallelism strategy. We have introduced TP8 and EP2. The meaning of TP8, EP2 is listed in the second table. For example, for attention modules, we have introduced TP8. For MOE sparse experts, we have introduced a mixed TP4 and EP2. For MOE's shared experts, we have introduced TP8, while for Fuse 8 GEMM and router GEMM, we have introduced DP8. Now, let's put all things together to give more details. We have drawn a layer-wise diagram to show our implementation, and let's take in the MOE layer of decoding phase as an example, because this layer has taken the most end-to-end performance. The first module is input module. As I have said before, the input is a BF16 tensor with shape 4 by 7K, where 4 is the number of tokens, and the first token from byte size 1, and the other 3 tokens from MTP layers. And 7K is the model's hidden size. The input tensor will be fed to Fuse 8 GEMM. And for our Fuse 8 GEMM, we have concatenated the weights of WDQ, WDQV, and WKR to reduce the kernel launch latency. And we can refer to the DeepSeek V3's technical report to check what's the meaning of WDQ, WDQV, and WKR. For example, WDQ represents the down projection of query tensor, while WDQV represents the down projection of KV tensor. The output activation of the Fuse 8 GEMM will be split into 3 parts. The first part is for query tensor, and the second part is for KV tensor. The first and the second part will feed to 2 Emerson norms kernel, and these 2 Emerson norms can be overlapped by multi-streams. Let's concentrate on the query tensor path firstly. The query tensor will be fed to the UQ-QR GEMM, and this GEMM we will concat the WQ and WQR weights to reduce the kernel launch overhead. The outputs of the UQ and QR GEMM will be fed to the WK in a batch GEMM. And please be of note, WK represents the up projection GEMM of KV tensor. And here, we have reassigned the path from KV path to query path to reduce the memory load overhead of KV cache for attention kernel. And the other point is that we avoid absorbing the module 3 and module 4 to prevent the weight size inflection and to avoid the actual weight loading costs. And now, let's turn to the KV tensor path. The KV tensor will be concatenated with the WKR path firstly, and then there is a fused applied rope kernel. And for this kernel, we will merge the KV tensors, the K tensors applied rope and the query tensors applied rope together to reduce the kernel launch latency.
Hey,
After
Kofeng. I just want to take a short pause here to remind everyone this is not only a sharing material, but it's a Q&A. So if you have questions, please ask, and Kofeng and or the rest of the team can answer them when they can.
Yeah. Thanks, Zach. And thanks for any suggestion, question, and discussion. All right. If no question, I will continue. Is that okay, Zach?
Yep, go ahead, continue.
Okay. Aside, when query and KV tensor are ready, we will feed them into our attention kernel. For this kernel, we have fused the BackGEMM 1, softmax, and BackGEMM 2 into one kernel. And this kernel performs multi-latent attention during generations. And it's acting like an MQA with num query heads as 16 here. The output of the attention will be fed to the UV batch GEMM. And the output of the UV batch GEMM will feed to the last dense GEMM, our output projection GEMM. And again, we do not absorb the module 7 and module 8 to avoid the increasing of weight loading overhead. After output projection GEMM, we will feed the output to an fused kernel. And for this kernel, we have fused one-shot AllReduce, add RMS norm, and dynamic quant in a kernel to reduce the kernel launch overhead again. There are two outputs of this fused kernel, NIP4 and BF16. The BF16-based activation out will be fed to the root GEMM firstly, and then top key module to calculate the top 8 experts for each token, while the MVP4-based activation out will be fed to the MOE module. There are two paths of MOE module. The first path is a shared expert. It's a dense GEMM-based path, and this path can be overlapped within root GEMM, top key, and sparse experts by multi-streams. And the other path is the sparse expert. For sparse experts, we have introduced a group GEMM or batch GEMM in our implementation. And this represents lots of experts. And for each expert, we will dispatch the tokens calculated, the corresponding tokens calculated by top key module. And after the ME module, we need a local reduction and a global reduction to reduce the same tokens activation out, but dispatched to different experts. And again, here we have fused all things together to fuse the local reduction, the one-shot reduce, and the add amongst norm operations together. That's quite a big diagram, but we have put all things in this diagram, such as our parallel strategy, our precision, our fusion pattern, our kernel connection. I will pause if there is any question.
I don't see any questions. Again, this live stream is really for everyone attending. So if you have questions, feel free to ask. But I don't see any right now. So Kofeng, you can go ahead and continue.
Okay, cool. Okay. After the configurations, let's step into the key feature. The first feature is MTP. Actually, we have explored 3 patterns of MTP. The first one is named as MTP Vanilla. The second MTP Eagle, and the third is MTP Relaxed Acceptance. The MTP Vanilla is quite straightforward. We just duplicate the MTP layers weight and cascade them with 3 layers. And it has bring us within accept rate with 2.49. And besides the vanilla version, we also explore the Eagle version. For Eagle version, we have introduced the auto-regressive style. So the Eagle version has the same cost as vanilla, but we will achieve higher accept rate, and thus the better TPS per user. The both of vanilla and Eagle versions are lossless. The third pattern, relaxed acceptance, is a lossy method. The methodology is that based on our observation, we think that we can relax the acceptance criteria. For example, we can generate more candidates during the decoding phase. And based on our exploration, if we generate 10 candidates and set the criteria delta as 0.6, we can improve the acceptance from 2.8 to 3.1 again, which means that we have another 0.9 speed up. And of course, it's a lossy method. So we have compared the accuracy without relaxed acceptance and with relaxed acceptance in the third table. And if we compare the table, we have to say that the accuracy loss is slight. The second key feature is the attention module. We have introduced lots of observations here, such as for kernel fusion. We have fused the BM1, softmax, and BMM2 into one gene attention kernel. We also fuse the applied ROP of K-tensor and query-tensor into one kernel. We have also introduced the multi-streams to overlap some kernels, such as the concat KV with UQ and QR GEMM, such as applied ROP with UK byte GEMM. This is work in progress. And such as overlap to Armstrong norms. The next key feature is about dense GEMM. We have chosen the two DP-based GEMM to optimize the Fuse 8 GEMM and Router GEMM because, the two GEMMs cannot be sharded by multi-GPUs, and we need to optimize them, or they will be bottleneck. We have written two customized kernel, and as shown in this perf comparison figure. For our workload scenario with tokens 4, our kernels have better performance than the default PyTorch implementation. And there are another highlights of these two kernels. For Fuse 8 GEMM, we have enabled the weight prefetching into shared memory with the help from programmable dependent launch. It's a specific feature of NVIDIA GPU. Specifically, once the previous AllReduce kernel is launched, we can trigger the launch of this Fuse 8 GEMM kernel. And the Fuse 8 GEMM kernel can prefetch its weight into shared memory immediately because the weight is not dependent on the output of the AllReduce kernel. And once the AllReduce kernel is done, it will tell the Fuse 8 GEMM to load weight from shared memory and load activation from L2. And we can speed up the memory loading by this method. For Router GEMM, the highlight is that we have introduced the AI code gene generator. In other words, the kernel is fully written by our AI code gene generator. It's the first time that we have introduced the AI code gene generator in TensorRT-LLM. It's a nice try.
Hey, Kofeng, I think there's a question that's finally popped up. I can bring that up and you can address it.
Okay. I think the first one.
So Kyla has a question. Could you elaborate on how DeepSeek R1's kernel level optimizations differ when using smaller batch sizes like 16, especially in real-time inference scenarios?
The kernel level optimization differ when using small batch size 16. Oh, I think for batch size for smaller batch size 16 rather than batch size of 1, we call it low latency scenario rather than min latency scenario. Most of the kernel optimizations can be applied to batch size 16, such as the Fuse 8, such as the optimization of attention kernel and the other kernel. But I must admit that for dense GEMM, for larger batch size such as 16, it may be carefully to using our customers the kernel. We have a heuristic from Python level, and if the batch size is larger than a value, we will fall back to the default PyTorch. We will fall back to the default kernel implementation. Is that okay?
I think so. There's a part 2 as well.
Mm-hmm.
I think you covered that. How are you optimizing load balancing, right?
Oh, I think I will discuss this in the following slides,
Okay.
especially for loading balance.
I think, Kyla, I guess just wait a minute and Kafeng will get to it.
Yeah, yeah.
Okay, go ahead.
Okay. The third key feature is AllReduce. We have written a customer's kernel named as one-shot kernel. And for this one-shot AllReduce, we have done more fusions, such as fuse local reduction or MOE, fuse IDE and Amos norm, and fuse dynamic quant or BRCT to NVIP4. And we have made a heuristic in the link. And this picture has shown our heuristic boundary. Or not, we have taken the Amos norm and IDE into consideration. And for our workload scenario with token 4 and hidden size 7K, of course, the one-shot AllReduce with fusion has better perf. Next one is about MOE. For this module, we support 2 backends now. The first one is Kala's group GEMM-based backends. And here, the main observation is named as sparse experts as GEMMs. For the old flow, for each input tensor, we need to dispatch the tokens to different experts. And we need to activate the group GEMM. And after the group GEMM, we need an index-based local reduction to reduce the same token, the activation out that are dispatched to different GPUs. The dispatch and the index local reduction are expensive for our scenario. So we have introduced sparse experts as GEMMs. The idea is quite straightforward. We can feed the whole input tensors to all activated experts without considering the redundant computation, because our total token is 4. And the active experts are heavily bounded on waiting, on loading, bounded on the loading the weight, no matter the token is 1 or token is 4. What we need is just to introduce a mask before local reduction, and this procedure will be filled into AllReduce. And with this optimization, we can remove the expensive dispatch and index local reduction from the old flow. Another backend is TRT-LLM backend, and it provides better kernel efficiency and more fusions. That's better perf. We have tried our best to provide a stable and best performance. For both of the backends, there is a common observation. We have introduced the multi-streams to overlap the shared experts with router GEMM, top K, and sparse experts. That is the observation of MOE from kernel level and system level. And for next slides, I will discuss about the load balancing. For MOE's sparse experts, we support 2 parallelism patterns as tensor parallel and expert parallel. I will discuss expert parallel firstly. For expert parallel, we will dispatch different experts to different GPUs. Here, the issue is that if for different GPUs, the activated experts number is different, we will have different weight loading on different GPUs, and thus different unbalanced workload. And this unbalanced workload will be exposed during the last AllReduce because there is a global sync among different GPUs. The other parallelism is tensor parallel. For tensor parallel, we will evenly split all experts' weight to all GPUs. And the tensor parallel will provide a balanced workload. But here, the issue is that we need to split among the small intermediate size of DeepSeek R1 model, such as 2K. And the group GEMM's kernel efficiency will be worse if we split them among a large number of GPUs. In other words, it's a trade-off between EP and TP, and we have introduced the mixed ETP here. And based on our heuristic, we find that the mixed TP4 and EP2 for sparse experts is a good trade-off between kernel efficiency and balanced workload. I think the next feature is CUDA graph and the programmable dependent launch. I will say it is very helpful when kernels are small, for example, for min-latency or low-latency scenario. And it's a necessary feature. And we have touched it in before slides, for example, based on CUDA graph and the PDL. Not only can we launch the kernel early, but also we can do some fancy work such as weight prefetching. And of course, we also fine-tune our clock and power for bad kernel heuristic. I think these are all details of our key features. And any question?
No new questions. But
Okay.
as a reminder, ask questions now while the team is online. This is kind of why we're here, and help developers and everyone who's attending with any kind of questions or issues you might have. All right, Kangfeng, you can.
Yeah.
Everything
All
okay?
Right. Yeah.
Oh, we did get a comment from thanking you for the explanation of load balancing.
Okay. Thank you. Thanks for the question. Load balance is a quite headache issue for us. Actually, I have to do more exploration for this. And we will do, of course, the more exploration.
All right. Should we move on?
Okay, all right. I think the next chapter is about our future works. I think we have got good performance, but it's still far from the boundary. The optimization works is still on the way, such as we can do more fusions, we can do more overlap, we can do more optimizations of attention kernel, and finally, we can introduce more aggressive MTP. This is about our future works. And I think we have open sourced our TRTM in GitHub. And thanks for your any suggestion, feedback, and discussion.
I'll post a link to the repo in the chat.
Okay, yeah. Yeah, it's about our reference. I think that is all.
All right. Is that it? Kofeng? Does that wrap up the what you wanted to cover?
Yeah.
Okay. All right. Well, we can stay on for a bit longer. We do have about 10 or 15 minutes left. So if you have any questions, please ask, now. If not, I posted in the chat our NVIDIA developer Discord and the TensorRT-LLM forum links. You can always go there and post your questions, concerns, anything that you might need to the team, and they'll try and get back to you when they can. So I don't see any more. Well, actually, yeah, I don't see any more questions coming in. I guess if that's it, then we can wrap up a little bit early. Just want to thank everyone for joining us today, and come back and join us for the next stream. I think it's going to be next month. We are also planning to have a wider developer town hall for other NVIDIA technologies as well. So please be on the lookout for that.
All right.
All right,
Thanks.
great. Thank you for joining us. Thanks, Kofeng.
Thank you. Thanks. Bye-bye.